If you've been staring at the periodic table, wondering how on earth all those letters and numbers translate into actual science, you are in the perfect place. Let's unlock the secrets of Unit 3 Chemistry.
Here is our game plan for today. We'll hit subatomic particles, electron shells, ions and the octet rule, isotopes and symbols, periodic table groups, and then wrap it all up with a massive chemistry cheat sheet to lock it in. Section 1. Subatomic particles and properties. Okay, let's zoom right into the atom itself, which is built from just 3 microscopic puzzle pieces.
Take a look at this breakdown. Notice how protons and neutrons are packing literally all the mass right in the center, the nucleus. Protons bring the positive charge, neutrons are totally neutral, but they both weigh 1 atomic mass unit, or AMU. Then you've got your electrons floating in the cloud outside. They have a -1 charge and pretty much 0 mass. They're practically weightless, but as we're going to see, they absolutely run the show chemically. Oh, and here's the golden rule to remember. Protons dictate the element's identity. If you change the proton count, well, you've got a totally different element.
Moving on to Section 2, electron configuration and shells. Because those electrons don't just float around randomly, they are highly organized.
Think of it exactly like VIP stadium seating. The row closest to the stage, it's tiny, holding only 2 electrons max. That's your first shell. Electrons always want the best seats, right? Closest to the nucleus? So, row 1 fills up first. Once those 2 seats are taken, the rest of the electrons spill over into row 2, which holds up to 8. And if that one fills up, they spill into row 3, which also holds 8. 2, 8, 8. Simple as that.
And this right here brilliantly illustrates valence electrons, which are the absolute VIPs in the outermost shell. Look at sodium on the left. It has 11 total electrons. 2 go in the first shell, 8 in the second, which leaves exactly 1 lonely electron in the third shell. That outer guy is the valence electron. Now look right next door at magnesium. 12 total electrons, so it ends up with 2 valence electrons in its outer shell. These specific valence electrons are absolutely crucial because they dictate exactly how an atom is going to react and bond with other elements.
Section 3, ions and the octet rule. So atoms are basically obsessed with having a full outer shell, and they will literally steal or give away electrons to get it. That brings us to this definition right here, the octet rule. This is your ultimate shortcut for predicting how neutral atoms transform into charged ions. Think back to sodium with that 1 lonely valence electron. To get a full outer shell, it's way easier for sodium to just kick that single electron to the curb, dropping back down to its perfectly full second shell, rather than trying to somehow steal 7 new electrons. When it loses that negative electron, the whole atom becomes positively charged, which we call a cation. On the flip side, if an atom steals electrons to fill its shell, it becomes negative, and we call that an anion. So let's use this visual cheat sheet to perfectly map out those typical ion charges just based on their group on the periodic table. Group 1 alkali metals, like our friend sodium, all have 1 valence electron, so they always form +1 cations. Group 2 metals have 2, so they lose both, forming +2 cations. Now check out group 17, the halogens. They have 7 valence electrons. They are so close to a perfect 8 they can taste it, so they aggressively steal 1 electron, becoming -1 anions. And group 18, the noble gases, they already have 8. They're totally satisfied, so they just stay completely neutral with a 0 charge.
All right, Section 4, isotopes and nuclear symbols. We know electrons control the charge, but what happens if you mess with the neutrons?
Well, remember, changing protons changes the element itself, but neutrons are a bit more flexible. When you change the neutron count, you get an isotope. Take carbon-14. Every single carbon atom in the universe has 6 protons. That's practically a law of nature. A standard stable carbon atom usually has 6 neutrons, adding up to a mass of 12. But carbon-14 has packed in 2 extra neutrons. That extra weight is exactly what defines a stable isotope versus a radioactive one. In fact, because carbon-14 is slightly unstable or radioactive, scientists can actually track its decay rate to carbon-date ancient artifacts. How amazing is that?
Now, when you need to write out a nuclear symbol for something like a sodium ion, just follow these 4 exact steps. It looks kind of complex, but it's really just a standard template. Step 1, slap the big element abbreviation right in the center. Step 2, put the mass number, which is protons plus neutrons, on the top left. Step 3, the atomic number, which is just the protons, goes on the bottom left. And step 4, if the atom gained or lost electrons, you write that overall charge on the top right. If it's totally neutral, you literally just leave the top right blank. Boom, done.
Moving to Section 5. Periodic table families explained. Let's apply all these micro rules to the macro map. The whole periodic table is really just organized by how elements manage their electrons, and there is a stark dividing line right down the middle. On the left side, you've got your metals. They desperately want to get rid of electrons, and all those loose flowing electrons are exactly why metals are so fantastic at conducting electricity. On the flip side, over on the right, you have your nonmetals. They are aggressively trying to gain electrons to fill their outer shells, and physically they tend to be brittle solids or just exist as gases. What's really fascinating here is how these abstract group trends connect to things you use every single day. Look at the group 1 alkali metals. They are so eager to shed their one valence electron that they will literally react violently, sometimes explosively, with plain old water. We actually harness that intense chemical energy to power the lithium-ion batteries in your phone. Then look at group 17, the halogens. They are incredibly reactive because they will do absolutely anything to steal just one electron to complete their shell. That intense, aggressive reactivity is exactly why we use chlorine to destroy bacteria in swimming pools. Now we can't forget the metalloids sitting right there along the staircase in the middle. They have this kind of unique identity crisis, possessing properties of both metals and nonmetals. They aren't perfect conductors like pure metals, but they aren't complete insulators like nonmetals either. That specific semiconducting property makes elements like silicon the perfect foundation for the microchips inside the very device you're watching this explainer on right now.
And then you have the noble gases in group 18, just sitting quietly on the far right. Because they already have full valence shells, they boast a zero charge and simply refuse to react. They don't steal, they don't share. They are basically the chemical snobs of the periodic table. This extreme stability is why helium is perfectly safe to put inside birthday balloons, and why neon gas glows so beautifully when we run electricity through it without, bursting into flames. Finally, Section 6, the final chemistry cheat sheet. We've covered a massive amount of ground today. So let's lock it all in before you sit for your exam. Seriously, take a mental snapshot of this table right now. It defines every major vocabulary term we just conquered. Protons are your identity. Valence electrons are the VIPs in the outermost row dictating your chemical personality. Lose an electron, you're a positive cation. Gain one, you're a negative anion. Tweak the neutrons, you get a new isotope but stay the same exact element. And those metalloids are the brilliant fence-sitters making modern tech possible.
To leave you with a final test of your new skills, based on everything you've learned about atomic mass and charge today, can you crack the code for neutral oxygen 16? Remember the rules. Atomic number dictates the protons. Mass is protons plus neutrons, and if it's perfectly neutral, the positive protons have to perfectly balance the negative electrons. Take a second, work the puzzle, and trust the rules you learned today. You've totally got this.